Hey guys, welcome to your next tutorial. I wanted to do an additional tutorial before we actually jump into the challenge video that went over vectors and what vectors are and how they can be useful. Vectors are really important for game development. They let you do physics, they let you do, motion, collision, all of those things that are really useful in any interactive game. So I wanted to make sure that I gave you guys a full tutorial dedicated to vectors, and at the end of this tutorial we'll use vectors to implement some really simple projectiles that we can shoot out of our little player. So first of all, what exactly is a vector? Well, at its simplest definition, a vector is just an array of numbers, and the number of elements in that array corresponds to the dimensions of the vector. So let's say we are using two-dimensional vectors. Since we're in a two-dimensional game, we have two spatial dimensions. We have width and height, usually coded as x and y. So our vectors for position, velocity, all of that, they're all going to be two-dimensional. So let's go ahead and draw our first vector. Let's go ahead and just put a point. I'm going to put a little point out here. And if you're familiar with any Cartesian coordinate plane, you know that we can write the location of this point using its x and y coordinates. And we'll just pretend this is at 100, 100. Really simple. Well, this point right here, this pair of numbers, this xy coordinate pair, is a vector. It's just a way of encoding, in our case right here, it's a way of encoding position. We're going to use a vector to encode position. And if you wanted to do it in code, you could use a GLM vec2. Now we can also do things with those vectors. There's lots of different operations we can do on vectors. Let's say we have a little person. I'm going to draw our guy in red. And let's make him really small, actually. I am a paint pro. And there we go. Here's our guy, and let's give him a head. So this guy, he has a position. Okay, let's mark his position, which will be the position that we store in his player class. We'll mark it as just the center of his body. It could be anywhere relative to him. We'll say it's the center of his body. Now we need to store this position in a vec2, a GLM vec2 or something like that. We're going to say he's at x coordinate 50, y coordinate 100. So this is his position in the world. Now let's say in our game we have explosions and a bomb goes off, we'll say down here. Now this explosion is going to also have a position, which we'll mark in blue with our little pencil tool here. And we need to store this position in a vector. So let's say this has x coordinate 100, y coordinate 50. Something really simple like that. Well, when this explosion goes off, we want to calculate if our player should get damaged. He should get damaged based on his distance from the explosion. The further away he is, the less damage he takes. If he's beyond a certain point, he really shouldn't take any damage. If he's really close, he should probably die. Well, how are we going to calculate his distance? Well, this is where vectors come in. What we want is we want another vector. We want to calculate the vector between the explosion and him. And remember, a vector is just, in our case, a two-dimensional vector is just two numbers. But we can draw vectors as an arrow. If we wanted to visualize his position as an arrow, what we could do is draw the arrow from the origin, like this. And let's use a different color. Let's use pink. So here's the position of the man from the origin. Here's the position of the explosion from the origin, visualized as an arrow. Now we can use simple geometry here. The length of this part right here, this little pink side of a triangle, is 50, obviously because his x-coordinate is 50. And the length of this part of the triangle right here is 100 because he's at y-coordinate 100. That's very simple. That's how coordinates work. If you've ever done anything with the Cartesian plane, you understand that you can form a triangle out of this. Well, similarly, we can form a triangle between the player and the explosion. So let's use purple. That's a better color, I think. First, let's draw the arrow from the explosion to the player, and then let's break it into a triangle. We can't just calculate the distance using just this right here. It would be hard to do. What we want to do is turn it into a triangle, because triangles are really easy. They're geometrically easy to figure out. There's formulas for them to where we can calculate distances and things like that. So what do we want? We want this. We'll call it A. We want the length of this side, because that's going to tell us the distance, the actual distance of the player from the explosion. Now we have two more sides of this triangle. We have a B and we have a C. Together, they make up the vector that is the distance vector between the player and the explosion. Well, how do we get this vector? Well, here's where some vector operations come in. We have several vector operations. We have addition, we have subtraction, we have multiplication, we have division. It's all basic stuff. And it's actually really, really simple. If we want to add two vectors together, we just add their components. So let's say we have the vector 20, 30, and we have the vector 50, 60. And let's say we want to add these together. Well, all we do is first we add the x components together. So what is 50 plus 20? That's 70. Then we add the y components together. What's 60 plus 30? That's 90. So the resulting vector is 70, 90. And this is what you do for all of the operations. For multiplication, you just multiply the components. For subtraction, you just subtract the components. So what we can do to get the length of b is we can subtract the y components. So let's go ahead and write that out. We're going to say b equals. Now let's take the player's y coordinate. That's 100. If we want to get the distance between the player's y-coordinate and the explosion's y-coordinate, we're just going to subtract them. So in this case, we're going to say b equals 100 minus 50, which equals 50. So b equals 50. What about c? Well, c is easy too. C equals, in this case, we're going to take the x-coordinate, which is 50, and we're going to subtract it from the y-coordinate, which is 100. But we're going to subtract 100 from 50. So what is 50 minus 100? Well, that gives us negative 50. And this is actually supposed to be an equilateral triangle, but I didn't draw it very good. As you can see, B and C are not drawn to be equal, but actually they are supposed to be equal, so excuse my bad art. So we have 50 and negative 50. If we take the absolute value, which means if we just get rid of the negative number, then they're both the same. The reason we have negative 50 in the x is because we are going to the left with our little arrow here, our C vector. We're going to the left. All right, so we have this new vector, 50, negative 50, and this vector is actually the vector A. So we can actually write this as the vector A equals, well, we probably shouldn't write it as A equals because that's going to make us think the side of that is. So we're going to say VA, that'll say the vector A, equals 50 comma negative 50. All right, well that's good. We now have the x and y coordinates of the player relative to the explosion, but we still don't know the distance. How do we calculate what A is? How do we calculate the distance of the player? Well, to do that, we just use the Pythagorean theorem. If you've taken a basic math class and you've learned about trigonometry or basic geometry, you'll know how to calculate the length of this third side right here. Let's draw it a little bit better down here. Let's draw it to scale where the sides are actually equal. There we go. So here's our triangle. We want to calculate A. And we have here negative 50 and we have 50. Well, there's a very simple formula that you should just go ahead and memorize. It's easy to remember. And that is A squared equals B squared plus C squared. And this is called Pythagorean theorem, from a guy named Pythagoras who figured it out. Now b squared and c squared are your two other sides, and a squared is the length of the hypotenuse. The hypotenuse is the diagonal part of the triangle. So let's go ahead and calculate this. We're going to say a squared, remember a squared is the same as a times a, so a squared equals, and this is going to be, we'll say 50 squared plus negative 50 squared. Just like that. Now, when you take a negative number and you square it, you get a positive number. So this 50 squared and this negative 50 squared are actually going to be the same thing. Now, to finally get A, we have to make sure that the left side is just A and not A squared. So what we can do is we can take the A squared and turn it into A by taking the square root of both sides. So we're going to say A, or the square root of A squared, which is the same as just A, equals the square root of 50 squared plus negative 50 squared, just like that. And we can just plug that into a calculator and get the answer, and then we have the distance the length of this A vector. Now we know the distance of the player from the explosion. We can use that in all our math. We can determine how much damage he takes. That's really, really great, and that's really easy. This is what vectors are useful for, but they also have another use, and that is for velocity and direction. So let's say we have our player here, and we want to shoot a projectile. We want to shoot a projectile towards this little green spot right here. Well, first, what we want to do is determine the direction of this projectile, so that we know, or the direction of this spot. We'll say we clicked here and we want to shoot a bullet toward it. So we're going to go ahead and calculate the vector here, which I told you how to do, right? We just need to turn it into a triangle, get the distance between the x and y components, and then calculate this vector right here. And then we'll have a vector with length a. So this is the length of the vector. And we also, of course, have the components of the vector. Now, what we want to do is we want to create a projectile object. We'll make it a little orange bullet thing here. And we want to launch it in this direction. And we need to give it a unique velocity and a unique direction. So let's go ahead and say we have a class bullet. Let's actually start coding. Let's start making our bullet class. Let's go to graphics tutorials. Remember, we're going to go ahead and make this bullet as part of the game, not part of the engine. So we'll go to graphics tutorials, add class. And let's make a bullet. All right, finish. All right, so here's our bullet class. Let's give it some private variables. So it's going to need a speed. It's going to need a speed of the bullet, and that'll determine how far it goes per frame. So let's go ahead and say float speed. And it's also going to need a direction. This is going to determine what direction the bullet is going in. And we're going to store that in a GLM vec2. So let's go ahead and include GLM. glm.hpp. So we're going to have a glm vec2 direction. And we can combine speed and direction to get the velocity. Velocity is speed and direction. Now, how do we get direction? Well, what we want to do is we want to get a vector that has a length of 1 that is pointing in the direction of our green blob. The reason we want it to have a length of 1 is because if it has a length of 1, then we're going to say that is a vector of unit length. It has no real magnitude. It's like holding the number 1. If you take 1 and you multiply it by any number, you get that number. Similarly, if you have a vector that is a length of 1 and you multiply that vector by, for instance, a speed variable, the new length of the vector is going to be equal to the speed variable, but it's going to be pointing in the same direction. What we can do with this is we can create a vector. We'll say this is our unit length vector right here, pointing towards the projectile. What we can do is say, well, let's say we want it to go 1 coordinate space per turn. Well, in that case, we're just going to multiply the vector by 1, and nothing happens. We just get this same vector. But let's say we want speed to be 2. What that means is every frame, we want the bullet to go 2 coordinate spaces in that direction, or we could say 2 meters or whatever. So what we're going to do is take this orange vector and we're going to multiply it by 2, and that's going to increase its length. It's going to double the length. Now every frame, we're going to move the bullet this much. We're going to say 2. We're going to move the bullet 2 in the x direction, and we're going to move the bullet, we'll say 1 in the y direction. If we doubled the speed, then we would be moving the bullet 4 in the x direction and 2 in the y direction. And this can be done by just taking the unit vector, which is a vector of length 1, and multiplying it by the speed, and then taking that and adding it to the position every frame. Because remember, you can add 2 vectors together. We can actually add a velocity to a position to get a new position. If we have, let's say, the position 10, 10, I haven't actually drawn in the right spot. So here's the position 10, 10. And we have the velocity, we'll say v equals 1, 1. This velocity is going to correspond to an arrow going diagonally to the up and to the right. If we, in one frame, want to add the velocity to this position, we're going to say 10 plus 1 and 10 plus 1, and we're going to end up with 11. And that's what we would expect, because we are going to the top right with a velocity of 1, 1. So in frame 0, we're at 10, 10. In frame 1, we're at 11, 11. At frame 2, we're going to be at 12, 12. See how this works? It's very, very simple. Vectors are really, really awesome. But I haven't explained to you how we're going to take this long vector and make it a length of 1? Well, it's actually another really simple thing to do. First, all we got to do is calculate the distance of the vector using the same calculations we did before. We'll call it d for the distance. And then we just need to take each of the components and divide it by the distance. So we're going to say, we'll say d equals, I'm not going to do the math. We're just going to say we have a vector, and it has an x-coordinate and a y-coordinate. To get a normalized vector, so we'll say the normalized version of v, it's just going to be x divided by d, comma, y divided by d. And that will turn this vector into a normalized vector, or a vector that has a length of 1. And we don't even have to manually do this math. GLM has a GLM normalize function that will do it for us. It'll do the whole calculation for us. It's so awesome. So let's go ahead and start implementing it. Hopefully you know a bit about vectors. I haven't taught you all of the vector operations. There's other things like rotations and stuff like that, but we don't really need to know about that for the first challenge video. And I've got a whole bunch of folders open. All right, so this is, let's see, Andromeda. Let's go to graphics tutorials. All right, and we have our bullet class. So let's go ahead and have a init function for it. So we're going to say void init. What else do we need? We also need a position, glm vec2 position. We're going to need a void draw. And let's actually pass in the sprite batch and just have it draw itself with the sprite batch. So include Benjin. What's going on here? Benjin, there we go. Sprite batch. There we go. So the draw function will take a, let's say Benjin : sprite batch. And we're going to pass it in as a reference. We want to pass the sprite batch in, not a copy of the sprite batch. And we'll pass it in as sprite batch. So the draw function will just basically tell the sprite batch to draw itself. The init function is going to take a position and a direction. So glm vec2 position, glm vec2 direction, and let's also give it a speed, float speed. And why are we getting an error here? For no reason. All right, so let's copy this into bullet.cpp. Zoom in here. So the init will be simple. Position equals pos, direction equals dir, and speed equals speed. Now for draw, oh, and we have to say it belongs to bullet. Now for draw, if we go into main game, we can remember how our drawing works. So if we go to main game, we have the spritebatch.draw function. Takes a texture ID, the color, all of that stuff. Let's just kind of copy this and take it into bullet. So let's make a color. Color, actually it's Benjin color. And we'll just draw it in white. Now for pos, we're going to use position. For UV, we actually should just go ahead and use the same UVs we were using in main game. So we'll copy this. And for now, since I'm lazy, I'm going to go ahead and just use, like we did before, a static texture. This is really bad practice. We don't want to just use a static GL texture in here. We want to actually make it something that you do on the init, for instance. You can pass in what the texture is or something like that. But we're being lazy here, and we're just trying to implement something really quick to make sure that it works. So let's go ahead and up here, let's include, and we need Benjin resource manager. And we also need include Benjin, oh, what else do we need? What is it complaining about? Sprite batch should not be underscore sprite batch. I believe that is all we need. Sprite batch wants a vec4. That's correct. So remember, sprite batch also wants the size. So let's make a glm vec4, pos and size, and we're going to say that equals a new glm vec4, where the x and y are position.x, position.y, and the width and height we'll say is 30 and 30. That's a good guess for now. And we'll just pass pos and size in. All right, so there we go. Here is our bullet.draw function. And we have an init. And finally, we need an update function. We need to be able to update the position of the bullet every frame. So we're going to say void update. And we should also probably give the bullet a lifetime. So let's say float, we'll say int lifetime. It'll be the number of frames. And we'll say int lifetime here. Let's go ahead and change that in the init function so this doesn't fly forever and lag our game. We'll say lifetime there, and lifetime equals lifetime. This is just temporary code. You don't even need to really follow along if you don't want to, though I would recommend that you follow along so you know exactly what I'm doing. What did I do? I need a semicolon here. And let's copy the update into the draw function, or sorry, below the draw function. All right, bullet colon colon update. Now, what do we do here? Well, every single frame, all we need to do is say position plus equals, and we're going to say direction times speed. Now remember, direction is going to be a vector that has unit length, so it's going to be like taking a vector 1 times the speed, and then adding that to the position every frame, and that will move our bullet across the screen. If we wanted to get fancy, if we were doing like a platformer, we could apply gravity here too. We could do all sorts of cool stuff, but for now we're going to be just really, really basic. So let's go to main game and let's get some bullets. Let's go to maingame.h. I'm losing it. There we go, maingame.h. Let's include our bullet class. All right, and let's make a vector of bullets up here. So we're going to say std vector of bullet, and we'll say bullets, like that. So this is going to keep track of all of our bullets. Anytime we want to add a new bullet, we just add it to this vector, and we'll have all the bullets get updated in our update loop. So now let's go to main game, and let's start by in spritebatch.draw, let's loop through all the bullets. So for int I equals 0, I is less than bullets.size, I plus. We're going to say bullets I dot draw, and we're going to pass in sprite batch. Remember, it's a reference, so it's going to pass the original sprite batch. Now we also need to update all the bullets. So here we are in the game loop here. We'll just do it right here before draw game. For int I equals 0, I is less than bullets.size, I plus. And we're going to say bullets I dot update. And we forgot to implement lifetime here. So let's go ahead and every single time we update, we're going to say lifetime minus. And then we'll say if lifetime is equal to 0, then let's tell whoever updated us that we need to be destroyed. So let's change this to a bool. Let's put a little comment. Returns true when we are out of life, so when we should be destroyed. So if lifetime equals 0, we're going to return true. Otherwise, we're going to return false. So we'll make that a bool. So now our main program, maingame.cpp, whenever we do bullets.update, we can say if bullets.update is equal to true, then we can delete this bullet. We don't need the bullet anymore. So when that's the case, we're going to just do the trick where we swap it with the last element of the vector. So we're going to say bullets I equals bullets.back, and then bullets.popback. Hopefully you remember this trick. It's a good way to remove elements from a vector when you don't care about order. But now because of this, we're going to skip over the bullet that is in the bullets.back, because we're going to have bullets.I equals bullets.back, and then we're going to call I plus. So bullets.back is never going to get updated. That's not what we want. Instead, we can stop doing I plus here, and we can do an else I plus here. So we're only going to increment I if we didn't delete a bullet. There we go. So this will update all bullets. And finally, whenever we click, we need to add a bullet that is in the direction of where we clicked. So we can do that down here, and we can do that anytime the SDL button left is pressed. Even when it's held down, we can just shoot 1,000,000 bullets or something like that every frame. That'll be kind of cool. So we already converted the mouse chords here. We have the actual world coordinates. And we're going to, just for simplicity, we're going to assume the player is always standing at the center of the world. Now, normally that's not what you want to do. Normally we would say the vector, actually let's go ahead and let's just do it properly. We're going to say glmvec to player position and it's 0 since he's at the center of the world. So the player starts out at 0. And then we're going to say, we'll say GLM vec2 direction. This is the direction from where we click from the player. So remember, it's that, oops, did I close Paint? Come on, Paint. So remember, if we have our little box here, and here's our little player, whatever. It's terrible. And we click here. I'll draw a little X here. If we click here, the direction vector is going to be this blue vector pointing from our player to the red X. And this is how we're going to determine the direction the bullet should go. So the vec2 direction is going to be equal to the mouse chords, which is a vector 2 of where we clicked, minus the player position. And since our player is always at 0, that's easy. But whenever we have a player that actually moves around, we just change this. Now we want to normalize the direction. So we're going to say direction equals GLM normalize direction. Now remember, what this does is it takes the vector, it does all that division, it does the Pythagorean theorem, everything, and it turns direction into a vector that has a unit length. And finally, we're going to make a new bullet. So we will call bullets.emplaceBack. And if we look at our bullet constructor, we will see, oh, we don't have a constructor, so we just have to make a new bullet. That's right. Let's, instead of using an init, let's just do this in the constructor. It makes more sense that way. So I'm just going to copy that there. I'm going to delete the init function. I'm going to go into bullets.cpp, and I'm going to take this, copy it here, and I'm going to copy these here. I'm not going to do the initializer list just because I'm being lazy, and this is temporary code anyways. There we go. So now we have it with an initializer, or sorry, with the constructor. So we can call in place back. So we're going to do position, direction, speed, lifetime. So the position is going to be mouse chords. The direction is going to be direction. The speed, let's start with something really small, 0.01f. That may be too small, but I have no idea. We'll have to test it out and see. And finally, the lifetime, let's make it 1,000 for now. Let's make it really long. Okay, have we forgotten anything? I don't believe we have. I think we're going to be shooting a bunch of Jimmy jumps out because we didn't use a different sprite, but let's just go ahead and see what happens. Hope it works. Oh, and it looks like I have gotten it backwards, but we are spawning people, and they are not moving at all. We're just kind of spawning them using the position of the mouse click. Of course, we don't want to spawn them at the mouse chords. We want to spawn them at the player position. So instead of spawning at mouse chords, we're going to spawn at the player position. And let's increase the speed and see if it's actually going to move. And let's check, make sure we are updating all the bullets. Game loop. Yes, we are calling bullets.update. And if we go to update, we are increasing the position. Yes. All right, so let's try that again. There we go. Now I'm shooting a bunch of these guys out, and as you can see, when I click up, it goes down. When I click down, it goes up. That is because in the previous tutorial, it looks like I actually forgot that since the y-axis is reversed, we need to actually reverse the y-axis in our little window class. So let's go ahead and do that. Let's go to our camera. Where is it? Camera2d.cpp. So here where we did convert screen to world, before we take the screen coordinates and do all the subtraction, let's invert y coordinates. So invert y direction. We're going to say screen chords.y equals screen height minus screen chords.y. And that should invert it for us. Let's try that again. Now it should shoot towards the mouse. There we go. Now let's make him faster. Let's change it to, where are we? Down here. Let's change it to, instead of 1 for the speed, let's change it to 5 for the speed. It's going to go 5 times faster. There we go. We're shooting a whole bunch of guys out towards the mouse. Isn't that cool? We can move the camera and it'll always go towards the mouse since we are computing the mouse coordinates. As you can see, I'm not moving the mouse. I'm just moving the camera around and it's always shooting towards the mouse. Now we could use this and we could actually collide these people with some monsters or bad guys and spray out blood particles and do damage and things like that. You could just have a lot of fun with this. You can make a bunch of different gun classes that each do different bullets and things like that. We're going to be using this in our challenge video in the next video to implement a zombie game where we shoot zombies, and it's going to be a hell of a lot of fun. Now, I haven't shown you how to do collision. I hope you can figure out basic collision on your own, either using Google or just playing around with vectors. I've given you everything you need to be able to figure out how two things are touching. But of course, in the challenge video, I will show you how to do it. I'm going to do it step by step so that you can learn exactly how to do it. And I think in the videos after the challenge video, we will expand the game to have text and sound and things like that, and we'll just have a lot of fun with it. Notice as the more little Jimmy jumps I spawn here, that it gets a little bit slower, but not too much slower because the sprite batch is pretty efficient. Our sprite batch is actually not as efficient as it could be. We have a lot of improvements we can make on it, so that'll be fun. We have a lot of really cool stuff we can do in the future. OpenGL is very powerful. C++ is very powerful. I hope you guys are as excited as I am, and I will see you in the next tutorial.